Good morning, everyone. Just gonna give a bit of an introduction. What do we mean by basically this IMASS standing for Itasca Model for Advanced Strain Softening? What do we mean by strain softening, and why is it an advanced model? And give it a bit of a background of our experience with IMASS and CaveHoek, and then talking about implementations and some simple examples. So when we use a numerical model to represent damage around an excavation or slope stability or caving, this simulation or this model must account for progressive failure of the rock mass and disintegration of the rock mass from an intact or jointed condition to a bulk material. And during this process, there are ample of factors that the constitutive model should address, and 4 of them being the most important to capture the most accurate representation of the rock mass in the numerical model are the cohesion and tension weakening and frictional strengthening, post-peak brittleness, the rate that we are basically softening or weakening the material, the modulus softening, and the dilational behavior. I'm going to go and touch base on each of these parameters later in the presentation. But the overall process of loading the rock mass to its peak strength and then softening or weakening the properties to a post-peak state using as a function of bulking and dilation is called strain softening process. And it's a result of using stress-dependent material properties in the constitutive model. So here I have an example, a conceptual model of caving to basically talk you through how this strain softening model or an overall strain softening model can represent the material behavior and how does it correlate to different state of the rock mass response. For instance, as we start from an elastic zone and in basically increasing the deviatoric stress condition, in the cave back, we are introducing damage to the rock. And basically what we are doing is that we are going from an elastic state into a state that we are slipping along the discontinuities, and we are doing some unsystematic crack growth within the rock mass. And as the stresses reach some certain level, at that point, we are starting to introduce damage to the rock mass in a systematic way. And by doing that, we are basically reducing the cohesion of the rock mass, mobilizing friction, and we are getting to the state that the rock mass is yielded, and at this point we call it mobilized post-peak. And at this state, the rock mass is completely broken, but it's completely interlocked. We can pick a block of rock out, but if we leave it there, the friction is going to hold it in place. And with increasing porosity, we are moving to a different state that the friction starts to reduce again, and we are basically bulking the rock mass, starting from 0% porosity somewhere here up to a maximum of 40% somewhere down the road, which is the maximum porosity a rock fill can contain. So the IMASS constitutive model has been developed to represent these rock mass phenomena, basically the response to stress change being rock mass yielding, addressing modulus softening, accounting for density adjustment, dilation shutoff, scaling of properties to zone size, because most of the strain dependent properties are basically zone size dependent as well, because the critical plastic shear strain that I'll talk about it later in the presentation is zone size dependent. And basically the IMASS constitutive model was developed using strain softening material model with strain dependent properties. And all of these strain dependent properties are available to the user throughout the simulation to see how the material behavior and the constitutive model is basically controlling those properties. Just a bit of a background, we have been using CaveHoek since about 2010, but we even have the history of using this strain softening material for simulation of caving and underground excavation and basically surface mining, even before that. Like it started in 2000 when we were involved in simulation of caving studies. But starting from 2010, as part of the industry-funded project, Itasca came up with CaveHoek to go hand in hand with its caving algorithm. And that's when we basically started CaveHoek. And CaveHoek was basically characterized by two bounding yield surfaces, just being peak and residual envelope. And we have been using that for the past 10 years, and we have learned so much more about the behavior of the brittle rock, and we implemented all our understanding and the new development into IMASS. That is our most recent constitutive model, and we have started using IMASS internally in-house for the past year or two to be able to basically learn more how this new constitutive model is being applied to our projects and our operations and our simulations. And now we are at the state that we are ready to commercialize it, and we are ready to basically release it to the public. IMASS, as opposed to CaveHoek, has actually two softening yield surfaces, basically three bounding limits that I'll go through it later. In addition to that, IMASS has material properties with new and unique names that basically distinguish, it categorizes different source of input parameters that basically look at, hey, these parameters are input, these are calculated from the input, these are flags, and these are emergent properties that are changing during the simulation, which makes it very easy for the user to keep track of these parameters, because it's a complex constitutive model and very comprehensive. So we don't want to lose the user when using these parameters during the simulation. And IMASS uses the latest Itasca Constitutive Model framework and techniques for apex correction, automatic testing, and property update and management. And I'd say I put this here as one bullet point, but this is a very important aspect of developing a constitutive model, especially the apex correction. Basically, what I can say is that the devil is in the details. Like, if we release the backbone of this constitutive model, people might be able to even code it themselves. But when it comes to using the constitutive model in an efficient way and making sure that it's replicating what we see in situ in the most accurate way, we have to make sure that when we are using the constitutive model in consulting, when we are transitioning from tension to shear, going from dilation to bulking, all of these are accounted for and are properly captured in the constitutive model. And we spend a lot of time making sure that in such a complex constitutive model, apex correction is done properly. So this is an overall view of the IMASS constitutive model. As you can see, we have three bounding yield surfaces. We have a peak envelope, we have residual 1, and a second residual. And for now, we are calling them residual 1 and residual 2. Before commercialization, we are going to distinguish these residuals from each other and have specific names for each other. We sometimes address this residual 1 as the mobilized post-peak strength, and residual 2 as the true residual strength of the rock mass. So if you look at the residual 1 and residual 2, most of the difference between these two residuals are basically at near zero confinement. Residual 1 represents a high friction angle at low confinement that's informed by the Barton's shear strength criteria for rockfill material. And as you can see, as you go from peak envelope to this residual 1, the friction angle is increasing. And as we go from residual 1 to residual 2 and reaching the true residual strength of the rock mass, this friction angle starts degrading again and going down. And if you look at it in a stress-strain kind of environment, you see after peak, we have a quick decay from peak envelope to residual 1. And after that, the rock mass behavior is being controlled by porosity and bulking, basically, a strain level corresponding to a porosity of around 40%. Every strain softening strain dependent material property would basically cease, and from that point on, it would be a perfectly plastic material. Okay, so let's now I'm just gonna give a bit of a more physical description of what each of these residuals are gonna mean, and then touch base on those 4 important parameters that we talked at the beginning, and basically go through them one by one. So As I mentioned, IMASS constitutive model is defined by 3 Hoek-Browne strand envelopes. By inputting GSI intact M from Hoek-Browne and UCS parameters, IMASS is going to automatically calculate the peak envelope for you. And the residual strand envelopes are basically two fits to Barton shear strength criteria for rock-filled material. And we are representing those with Hoek-Browne envelopes in our constitutive model. This is that shear strength criteria from Barton equation. And as you can see here, it's a function of normal stress, S is being the rock block strength, a basic friction angle for the rock blocks, and an equivalent roughness being this R value. And this R value from this graph is controlling what's the porosity that we are basically calculating those strength envelopes for. In a physical world, that first residual envelope represents the mobilized post-peak strength. At this point, the rock mass is assumed to have undergone fractions. Basically, fractures propagate through the rock mass, form rock blocks, but they're completely interlocked and they have 0% porosity. The second residual envelope represents a true rock mass residual envelope, where this degree of interlocking of the fragments is at minimum, basically being at porosity of 40%, that the rock mass can't go above that anymore. And this maximum porosity is user defined. You can limit it to 30%, to 20%, to whatever you want. Basically, the first and second residual envelopes describe the behavior of cohesion-less, perfectly frictional material with different degrees of interlocking. So the last point I talked about it. So let's look at the cohesion weakening and frictional strengthening component of the material. This is a pretty famous figure. As we know, as we start accumulating damage in a rock mass, reaching peak envelope and then post-peak, cohesion component of shear strength is going to decay and the friction is being mobilized on the surface of new fractures. Basically, we are increasing friction angle. And that is what we have here. Basically, starting from peak envelope, going down in cohesion, but we are increasing the friction angle. If you look at the slope of this line at 0 or near 0 confinement, we are mobilizing friction angle. But then as we go past that envelope and we are basically starting to bulk the rock mass, the friction angle is going to decay, going from this blue envelope to the green envelope. And that is an important part of IMASS. I'm not aware of any other constitutive model to have three bounding limit and 2 residual envelope. If you only had 2, you could only mobilize friction angle and stay at that high friction angle. And it's giving you a false sense of true residual strength for the rock. And as we will see here, as if you only had 2 residual envelopes, you would be stuck in this area and you can't go past into the bulking of the rock mass. And something that I need to mention here is that this is a conceptual model of caving, but it applies to underground excavation, underground mining, surface mining, slope stability. The only difference is when you reach this state, how far out you would bulk. Probably for slopes, this is going to be very limited. For underground excavation, is going to be very limited. But the only difference is how far down in this area you would go to bulk your material in the mobilized zone. So the post-peak brittleness, basically how fast you decay your properties. As we know, like going from peak to residual 1, as you can see here, is controlled by critical plastic shear strain. That critical plastic shear strain is amount of plastic shear or accumulated plastic shear you need to go from peak strength to mobilized post-peak strength. Unfortunately, there is not that much literature available in this regard. What we have here is that to give for greenfields operation and for when we don't have data to calibrate this property, because at the end of the day, it's a calibrated property to match what you see in your numerical model with the field measurements, damage, depth of damage, closure strain, and all of those for predictive modeling. But if you don't have a starting point, based on some of our work with mass mining technology, industry-sponsored project back in 2000, looking at some of our case studies, Lauren and Matt Pierce came up with this equation that basically give you an estimation of what this critical plastic shear strain is going to be for your material based on GSI. And what you can see here is that this is zone size dependent, and it honors the fact that this strain softening material is a function of the behavior is a function of the zone size as well. So this is being automatically calculated for different zones, and the user is able to actually alter it. And you can see the importance of this parameter. This is a drift being excavated with 5-meter span at 1,000-meter depth. And the only thing that we have changed here between the three cases is the multiplier for this critical plastic shear strain. Here we are using a multiplier of 1, don't change it, and we are not changing it at all. We are reducing it by an order of 10, and we are reducing it here by an order of 100. And what you can see is that the depth of damage changes from 2 meters to 3.5 meters. And also the closure strain is a big function of this ECRIT as well. So now that we are here, let's look at the cohesion weakening and frictional strengthening property in these models as well. You can see here that the cohesion is being decaying around the excavation surface as a function of how far out, or as a function of how much damage is being introduced to the walls, depending on how far out it goes in. You can see in the far field cohesion is around 6 MPa, and when you get to the surface, it goes down to around 500 kilopascal. Similar thing for mobilization of friction angle. In the far field, the friction angle is around like 25-30 degrees, and as we get to the surface, and we are basically mobilizing friction angle on the fractured rock mass, we are getting up to around 65 or 70 degrees, depending on how much damage we have introduced to the outer shell of the excavation surface. So past residual 1, the behavior of the model is controlled by bulking. This bulking is the change in the volume over the initial volume of the zone, or a function of porosity. And the beauty of this approach is that you can move, your strength envelope can move between this point C and D as a function of the volumetric strain increment or bulking on the other hand. Then this would capture the strength gain due to recompaction, or strength loss due to basically introducing more bulking to the rock mass. So you can basically move back and forth between here C and D. So this is an example for a block cave operation, and this dashed line, this area represents an old cave that the mine has propagated the cave, but then they ceased production for a while, and they went through this time-dependent phenomena of recompaction in their cave material. And at the bottom, you see the extraction levels. So what we did was that we could initialize this bulking, or VSI, or volumetric strain increment, in this old cave and see how it would affect the propagation of our new cave. So if we didn't change anything with VSI of 0, it basically means the porosity hasn't changed at all, and it would basically put us at this strength envelope, as you can see, the yellow one. But if you introduce a higher porosity to this material and show lower recompaction, it would bring you to this lower strength envelope here, the red one, and it eventually can go all the way to the black line as the true residual strength of the material. And here you can see the effect of that assumption for compaction on the propagation of a new cave, the neighboring cave there. And it's really important to realize that we wouldn't have been able to capture this if we didn't have that second residual in the model. Another important thing is the modulus softening. As we know, as a rock mass bulks while shear rotation, it is expected to experience a drop in modulus. And representation of this drop is really important in the model because it allows for stresses to shed away from the bulk area to the surrounding area, or if the material recompacts between that 0 to 40% porosity, it should be able to absorb some more stresses to simulate recompaction. So this is basically what we are doing here in IMASS, basically using Pappas and Mark relationship, showing that the rock drop is a non-linear fashion as you accumulate bulking in the rock mass. So you start from this initial rock mass modulus calculated from Hoek and Dietrich's relationship. As a function of bulking, we'll reduce it to a percentage like 1 or 2%, like eventually at 40% porosity, it can go up to around 200 or 300 MPa. And it's also a function of that decay in the modulus after 15 or 20% porosity is a function of intact UCS of the material, and that's what we are showing here as a sensitivity. And to remember that this modulus is constantly being updated via the zone-based volumetric strain to allow for this stresses being shed away from the very soft zone or being attracted again when recompaction happens. This is an example of another cave to show the modulus softening. On the top, this red area and this green and blue area are different geologies, but down here where it's orange, this used to be around 10 or 10.5 GPa for rock mass modulus, but you see as we get closer to the cave, especially in this area, the modulus goes down to around 1 or half a GPa. And where it's green here is because the rock mass was treated with hydraulic fracturing, and we would limit how much the material can bulk or actually soften due to modulus updating. So that's another powerful tool that, depending on different treatments in your rock mass, you can limit how much the material can bulk and how much softening or weakening it can undergo. Another important factor, as I mentioned earlier, is the dilational behavior. We have already implemented a dilation model that would change the dilation angle for zones constantly as a function of confinement and porosity, because we know that these are correlated. Another important factor in IMASS is that we have this sloss, which is an indicator of damage. So basically what it tells us is that how far along between these points, between B to C or C to D you are. Like, so you start from an sloss of 1, going from peak to residual 1, you would reach sloss of 0, and from residual 1 to residual 2, you would reach sloss of -1. So basically going from 1 to 0 to -1, and it gives you an idea how far along from your strand envelopes you are, and it gives you an indication of damage within your rock mass. So basically, when you're at 1, your rock mass has the full cohesion, and basically friction is starting to get mobilized. At residual 1, you have the highest friction angle but no cohesion, and at residual 2, you are at the lowest friction angle and no cohesion, which is the true rock mass. In this case, the sloss is shown for the zones in the vicinity of a drift in 2 different galleries. And as you can see, the sloss goes down to around 0.5, which is between peak and residual envelope 1. And it shows you where you are expecting damage. This is showing damage being focused in the corners of the gallery, or in this case, the damage is being focused around the intersections of the gallery. There are much more features in IMASS that just the time doesn't allow to go and cover all of those. One of those being density adjustment, which is very important in caving simulation. You can simulate weakness planes in IMASS using ubiquitous joint in Flag 3D. So it basically has that hierarchy structure that it can borrow ubiquitous joint from Flag 3D. Critical plastic shear strain can be defined for zones individually. It's not like the past that you can only define this critical plastic shear strain as tables. It's a property for each individual zone that you can go and alter, and a user-defined residual envelope can be used. Just about installation and usage, IMASS is built into Flag 3D7 and 3D7. You don't need any DLLs. It's built in. The IMASS version can be queried as a model parameter. It helps us when the users have some issues with it, they can just query the version of IMASS and we know what version of IMASS they are talking about, because this is an empirical constitutive model, and things can change if you find a bug or we need to change some small part of the constitutive model. So we need to make sure that when you're interacting with the users, we know what version of IMASS we're talking about. To invoke the model, as you can see, we only need to specify, okay, we are configuring IMASS, assigning the model, and we only need to specify these 5 properties to engage all the default behaviors on the zone. Obviously, you need to calibrate the model depending on your application, but it's not a very we didn't want it to be a confusing constitutive model for the users. You can see we have a lot of properties in this constitutive model, but just to get started for a simple model, these are the only 5 properties that you need to get started with.